Welcome to videos on filters. So this is a second part of videos on filters. So we were looking at the frequency response of Butterworth low pass filter for various order of the filter. So as we know that from the frequency response, if the art of the system, art of the filter is 1, the flatness is there for a very small duration from that DC frequency. You can see the flatness is keep on increasing as the order of the filter increases. So as the order is 10, you can see, so it is flat till this frequency, which is 0.8 of omega by omega p. On the x-axis, you can see it's a normalized frequency in terms of radian per second. So instead of giving this in terms of frequency omega, it is omega by omega p. So this happens to be the ratio of 1, which corresponds to omega is equal to omega p. So when omega is equal to omega p, which corresponds to the edge of passband. So edge of the passband happens to be omega is equal to omega p. Omega divided by omega p is equal to 1. So at that frequency, we have the magnitude as 0.707 over here. It is surprising to see all the orders of filter, which is 1 to 10, will pass through the same point of this magnitude of 0.707 when omega by omega p is equal to 1. So let us try to design a filter. Let us try to see the different equations required to design a filter. Now this is how to calculate the order of the filter. We know that the magnitude of the transfer function of a nth order filter is given by 1 over under root of 1 plus epsilon square into omega by omega p to the power of 2n, where this epsilon will going to represent what is the allowable variation in the amplitude in the passband. So as we can see that, so by substituting omega is equal to omega s, so which corresponds to the magnitude at the edge of the stop band. So magnitude at the edge of the stop band can be written in terms of dB as minus 20 log of 1 over this, or which can be again written as 10 log of, so by taking this square root outside and taking this denominator onto the numerator, this will become plus here, and this will become 10 log 1 plus of epsilon square into omega s by omega p to the power of 2n. So if we know the value of epsilon, omega s and omega p and order of the filter, we can find what is the A minimum, or if you know what is the magnitude that is minimum required. So if you know what is omega s and omega p and epsilon, we can find the order of the filter n. So let us take some examples in the coming videos and try to understand the usage of these equations. So let us, at the edge of the stop band, omega is equal to omega s. The attenuation of the Butterworth filter can be obtained by substituting omega is equal to omega s. That is the same expression here. This equation can be used to determine the filter order required, which is the lowest integer of n that yields A of omega s should be greater than or equal to A minimum. So we shall actually take up some examples to design a filter and try to understand what are these conditions mean. So this is what is the filter equation. The magnitude is magnitude of the filter equation of nth order filter is given by this. When omega is equal to omega p, we end up with this equation. This ratio becomes 1. So the magnitude at omega is equal to omega p will be 1 over root of 1 plus epsilon square. So that's what is Amax is given by 20 log of this, and epsilon can be written as under root of. So if we know the value of Amax, we can estimate the value of epsilon. If we know the value of epsilon, we can find Amax. So conversely, we can find the epsilon by knowing the value of Amax. So this is how we can estimate the value of Amin. So Amin can be written as this expression. So if we know what is epsilon, omega s, omega p and n, we can estimate Amin. Suppose if we know A min, epsilon, omega s and omega p, we can estimate the order of the filter. So this is what is A min. So from the maximum of the passband magnitude to the minimum required magnitude at the edge of the stop band. So this is the edge of the passband, this is the edge of the stop band, and this is Amax, maximum allowed variation in the passband. Now this is where how to locate the pole positions, the location of Butterworth filter poles. So we know that if the artery is N, we are supposed to have N poles should be located on the left hand side of the S plane. The first pole will be located on the circumference of this circle. The circumference of the radius of the circle is given by omega p multiplied by 1 over epsilon to the power 1 over n, which happens to be omega naught. That is the cutoff frequency. Omega naught is given by omega p multiplied by 1 over epsilon to the power of 1 over n. The first pole will be located at an angle away from the imaginary axis by pi by 2n. The adjacent poles will be always away by pi by n. So this pi is actually 180 degree. 180 degree divided by the order of the filter. So this is how the first pole is located from the imaginary axis, and the adjacent poles are away by pi by n. The first pole is always located pi by 2n away from the imaginary axis. So this is how it looks for n is equal to 2. Since n is equal to 2, so pi by 2n happens to be 45 degree. This is pi by 2n. Pi is 180. So since n is 2, so pi by 2n is it is 180 degree divided by 2n. Since n is equal to 2, we'll end up with this as pi by 4. Pi by 4 is actually 45 degree. Now the first pole is away from the imaginary axis by 45 degree. The adjacent poles is away by pi by n. So when it is pi by n, so since n is equal to 2, the two poles P1 and P2 are away by 90 degree. You can see this is 45 plus 45. This is totally 90 degree away from each other. This is located on the circumference of a circle whose radius is omega naught, which is given by omega p into 1 over epsilon to the power of half, because it is 1 over n where n is equal to 2. Similarly here, this is for n is equal to 3. With n is equal to 3, so pi by 2n. So pi by, now pi is 180 degree. So 2 into n happens to be 6 here. So it is 180 by 6. So it will be 30 degrees. So this will be 30 degree away from. So what is we have? This is 180 divided by 2n. So it is 2 into 3. It is 180 divided by 6. So it is 30 degree. So this is away from the imaginary axis by 30 degree. The adjacent poles are away by pi by n. So pi is 180, n is 3. So this is away from each pole are away by 60 degree. You can see this is away from this by 60 degree, and this is away from this by the 60 degree. And this third pole is away from this imaginary axis by 30 degree. I can see these two are equispaced from this P2. So it is 60 degree away. Here also it is 60 degree away. So this is an example for n is equal to 4. The first pole is away from 22.5 degrees. The adjacent poles are away by 45 degree each other. So this way we can locate the pole position. So let us see the summary of the design of a filter. For the given specifications like omega p, omega s, Amin Amax, first we are supposed to determine the epsilon value, which tells about what is the maximum allowed variation to have for the given filter. So since A max is given, we can effectively estimate the value of epsilon here. So once we find the epsilon value, since omega s and omega p are given and A max is also given, we can actually estimate the value of n. Determine the required filter order as the lowest integer of n from this equation. So we are going to estimate the value of n because we know this is a minimum, we know epsilon, we know omega s, omega p, all these are given. So we can certainly estimate the value of n. Next, we should determine the pole positions using the figure. So the figure what we discussed in the previous slides. Then determine the transfer function. So since we know the pole positions, so since they are on the left hand side of the S-plane, we can actually write their position and we can actually write the overall transfer function. Let us take an example where we have the omega FP happens to be 10 kilohertz, Amax is 1 dB and Fs is 15 kilohertz, and minimum attenuation in the at the edge of the stop band is 25 dB. The DC gain is 1. So we are asked to design a Butterworth filter which meets these specifications. So using this epsilon is equal to under root of 10 to the power of a max by 10 minus 1 for a max of 1 dB, this yields the epsilon to be 0.5088. Using this 0.5088 and the other values of a min as 25 dB and fs and fp as the given values here, the value of n comes out to be 8 point something. Suppose if you take the nearest possible value 8, it is 8.2 or 8.3. If it is 8.2, so it will be exactly 25 dB. If it is 8, it is 22.3 dBs. If it is 9, it is 25.8 dBs. Since we want to have more than 25 dB, so let us take the value of n as 9. If the value of n is 9, we are supposed to have now 9 poles. So 9 poles have to be located like this. Now this is the first one, second one, third one, fourth one. You can see there are 9 poles. So these are the 9 poles. But you can see the 1 and 9. The P1 and P9 are the complex conjugate. Similarly, P2, P8 are complex conjugate. And this P3 and P7 are again complex conjugate. P4 and P6 are complex conjugate. And this P5 is a real pole. We can actually find their location by using this. So how do we estimate the pole position of P1? It is as we know that, so this is the radius happens to be omega naught, which is, since we know omega p, since we know the value of epsilon, we know the value of n, we can actually know the radius of this. So once we know the radius of this, and we can find what is this position on the real axis and on the imagined axis. Since the angle of this, it is from this reference, it is 80 degrees. So we can actually find this real value and imaginary value using this equation. The real value is on the left hand side, it is omega naught into uh, minus cos 80 degree, and the imaginary value is plus j sine 80 degree. So this is by using the adjacent and the opposite sides, we can actually locate the position of P1, its real value and the imaginary value. So P1 is located at minus 0.1736 plus j 0.9848. So this is the location of your P1. Similarly, P9 is located exactly on the same real axis. The imaginary happens to be just minus. So if you take P1 and P9, so they are the complex conjugate. If you multiply those two, you will end up with a square plus s into 0.3472 omega naught into omega naught whole square. Just multiplying this with its complex conjugate, we get the quadratic equation corresponding to the P1 and P9. Similarly, we can find out what is the P2, since its real part is minus cos inverse of minus cos of now we can see this is 20, 40, 60, and the imaginary part is sine 60. So this is sine 60 and cos 60 is going to give the imaginary and real parts respectively. Similarly for P4, for P3 it is cos 60 degrees the real value, the sine 60 happens to be the imaginary, sorry, sine 40 and cos 40. For P4 it is cos 20 and sine 20 will going to be the real and imaginary values. So substituting all those things we'll get, of course this is the P5. So you can see the P5 is located at omega naught only. So that's why it is. So that's why this is of P5. This may be of this is of P1 and P9. This is of P2 and P8. This is of P3 and P7. This is of P4 and P6, this is of P5. So likewise, we can get the transfer function of the entire filter.